All right, guys, so I'm working on the review for the semester spring exam, and I'm working on number 4 right now. I just wanted to review the question, and then I'm going to go into solving for the answer. So this question states, how long does it take for a toy car to fall off the edge of a desk with a height of 1.34 meters? So when it says how long does it take, we're looking for time. And when it says the height of, that's 1.34, and that could be delta x, delta y. In this case, this is going to be delta y because we're talking about falling down, and it mentions height. So you could put an h or you could put a delta y right here. Either way will work. The car is moving at an initial velocity of 1.73, so that's going to be our VI, but it's also along the x-axis because it's going zoom and off. And I'll show you a picture of that in just a second. And then after that question mark, after we solve for time, then it wants another thing. It wants to know how far from the desk will the car land. So basically, we're looking for our distance on the x-axis. So you could put d, dx, you could put delta x, and all three of those will be fine for how you label it. So when you come to the drawing or the illustration of what it's looking for, first of all, we relabel what we have. I have the initial velocity on the x-axis. I know gravity is 9.8. I know that the delta y is 1.34, and that's pretty much all we have. We're looking for two things. In this case, we don't need to know how fast it's going to be going at the end. It doesn't ask us for that, but it does ask us for the time, and it does ask us for the distance. So, of course, we always solve for time first, and then we solve for the location where it lands. So here we are. Okay, this is where we're at. And what we're going to do is find out how far does it land, knowing that the distance from here to here, falling down, the delta y is 1.34. And we're going to say that the downward position and to the right is going to be considered our positive axis. So if we go up or to the left, we're going to call that negative. Okay, so that means we're going to use gravity as our positive number because we're going down towards gravity, so that's going to be positive. All right. So with that in mind, how do we solve for time? If you remember, the formula we use is delta y is equal to 4.9 t squared. And in case you were curious, where did we get that from? You have to remember, okay, that we had delta y is equal to VIY plus 0.5 AT squared. And it turns out since the initial velocity is 0, that goes away. And half of 9.8 is 4.9, and we're right back to where we started. So this is where we are starting from here because it's basically, our fundamental formula simplified to its most basic form. So our delta y we know is 1.34 meters in height, and we know we have 4.9 times t squared, and that's what we're solving for. This is our variable that is unknown. So since this is multiplied by this and we want to move it to the other side, we're going to divide by 4.9 on both sides. What we do on one side, we do to the other. These cancel out. 4.9 divided by 4.9 is 1, so we can cancel that. 1.34 divided by 4.9. That's where we're at right now, so I'm just going to look that up on a calculator. So I need my calculator real quick. 1.34 divided by 4.9 gives us 0.27346938. So what do we put down? Well, 3 digits for a basics physics class in high school is fine. 3 on the paper, 2 in the calculator, or 2 on the computer when you're entering in your answers are fine. 0.273 seconds is going to be our t squared. Now, we're still not done yet, right? This is where we got it from. This comes pulled down. All we had left was the equal sign and then our answer, and that's t squared. The opposite of a square is a square root because we have to get rid of that square. We only want time. We don't want the square of time. So when we take the square root of something, there's 2 ways of doing that. You can hit the second, and then you can hit this, and you can hit answer, or you can just put in the number that you had. And in this case, I'm just going to put in the 3 digits that we had, 273, 0.273. And I'm going to hit enter, and that's going to give me my answer. So I'm going to put, again, 3 numbers down, 0.522. 0.522. 0.522 seconds equals how long it's in the air. So that's not for very long. It's less than 1 second in the air. Considering that it's only 1 meter thick, a little bit more than that in height, of course it's going to hit the ground pretty quick. So now that we know how long it's going to be in the air, we need to solve for where it's going to land. So now we are looking for, from here to here, we're looking for the delta x. So if you remember, velocity equals distance over time. And of course, we have to label what kind of velocity we're talking about here. So if I move this over a little bit so you can see what I'm doing. Right. So now we're going to use, our velocity was 1.73. And that comes from over here when we were listing everything. We said that its initial velocity was 1.73. And that's going out this way. It's starting to fall from 0 and it's going to speed up, but that's on the y-axis. And we're only talking about the x-axis. So here we are, 1.73 is equal to, this is our Vx, to our distance that we don't know over our time that we do know. That's going to go right here. 0.522. You can put the 0 there, that's fine. Won't hurt it either way, as long as you have the decimal in the right spot. Okay, so to move this over so we can get our variable by ourselves, this is being divided by. So the opposite of divide is to, you got it, multiply. Okay, what I do on one side, you do to the other. So we're going to multiply by 0.522. Remember, this is in the numerator, that's in the denominator. So these will cancel each other out, leaving us with the distance on the numerator side on the top. So this is going to be over 1, so we'll have a whole number. So whatever this is will give us dx. So what is 0.522 times 1.73? So you can pause right here if you want to and put in your calculator and see what you get, and then you can look. This is what I got. This is how I put it in, and then I hit enter, and this is what I got for my answer, 0.90306. So we're saying that 0.903 meters equals distance, and that's because we're doing distance, so that means this must be in meters. So almost an entire meter stick away is how far that the car landed. Okay, and that's what you do each time. You need to start with this formula here, solve for time, then go into Vx equals dx over t. So this is the formula, and this is the formula that you use each time. That one and that one. Zoom out just a little bit here so you can see both. All right. All right, so I'm going to move on to number 5 now. So here's number 5. I'm going to zoom in so you can see the question a little bit clearer. Here we go. Number 5 says, draw a free body diagram showing what forces are acting on an object that is being projected from the top of a cliff. So basically we have this cliff right here, and I like using a circle because it's simple, and it's being projected forward at a certain velocity, and it's going to start to fall at an initial velocity of 0 going on the y-axis. Okay. And as we fall further and further and further and further down, our Vx is the same each time. Nothing changes on the velocity. There's nothing to stop the velocity. Remember, an object in motion stays in motion unless an unbalanced force is acting on it. Nothing is acting on this except for maybe air resistance. And in this case, it does not indicate that there's a lot of air resistance. So let's just put it in the ideal world where there isn't any. And so our velocities are going to stay the same, does not change. But we do know that the velocity of this object will increase because of gravity. So gravity is pulling on it, but then we also know that our VIY is going to increase as well. So basically we have two vectors. We have a vector going to the right, making it go to the right. We're also making it go down at the same time. Hence the two directions, which is why we call it two-dimensional motion. Okay, that's number 5. That's all there is to it. If you have any questions, give me an email or shout out, and I'll answer it to you as best I can. Number 6, draw a diagram depicting the direction of force, acceleration, velocity on an object moving in a circular motion. Okay, so first things first, we have a circular motion. Let's say it's a tether ball, okay? So I've got basically a center point, apex, and then we have the ball itself, let's say is at the arrow point, and it is moving this way, okay? As it does, okay, we know that it is changing, it's changing its direction, which means that its acceleration, we're going to say centripetal or circular acceleration is changing constantly, and that is because it is being pulled towards the center, causing it to continue in this motion. Because if we were to let go of this string, it would fly away, right? And where would it fly away? That's a good question. It would fly in this direction here, okay? Or at tangent to the line. So if I was to let go here, let's say, then my velocity vector would be here and it would fly down, or it would fly this way. Again, tangent to the circle. What does that mean? It means that my line, my vector line that I'm drawing is just barely touching the circular line. So tangent is like touching the circle line. We call this the velocity vector. So we're just going to put Vx because this is where it would fly off to. Technically, this would be the y. This would be Vxy. But just so you know, it is our velocity vector. This is our acceleration, centripetal acceleration vector, and then it also wants to know about the force. Force is a push or pull. Nothing is pushing on this, but we are pulling this string down to continue the circular motion. So also, our centripetal force is towards the center because we're pulling on the object, keeping it in that circle. So that's our three vectors. The force and the acceleration is towards the center. The velocity is wherever it would fly out if you were to let go. Those are our three vectors. Okay. Number 7. So for number 7, it says, what is the mass? So here we go. It asks, what is the mass? There's our question. They want to know the mass. What is the mass of the object represented in the graph shown above? So first we need to identify our axes. So on the x-axis, what does it say? It says force, right? So this is a force in newtons. And our y, let me zoom in a little bit here so we can see this a little bit better. Okay, our y is kind of hard to see because of the drawing that I did, but it says it is acceleration. So I'm just going to go like that, and that's meters per second squared. So nowhere in here does it mention mass. So how are we going to get mass off of force and acceleration? Well, if you remember from Newton's second law, force is mass times acceleration. Aha, there's mass right there. And we happen to have these other two variables with us in the graph. So how are we going to get mass? Well, just solve for mass first. So how do I get mass by itself? I'm multiplied by acceleration. So the opposite of acceleration is to divide. So what I do on one side, I do to the other. So this cancels out, leaving me with mass equaling force divided by acceleration. So we're going to pick one point on our slope. And let's just pick this point right here. I've got 0.5 for my force. And I'm going to go up to my slope. I'm going to find out where I am on the y-axis. And in this case, it would be 2. So I have A equals 2, and I have force is equal to 0.5, right? All right, so we're going to plug these numbers into the formula that we used to solve for mass. So my force, again, was 0.5. So I'm going to put a 0.5 here. My acceleration number is 2. So 0.5 divided by 2. Whatever that is will be our mass. And that happens to be 0.25, see? 0.25. So your question might be something like, well, what if I use a different spot? Well, all right, you should technically, because this is a straight line slope, all the slope on here should have the same answer. You should have 0.25 as your slope. Don't forget kg is for mass, because we're using our units, our universal units for physics, for science. So let's try it again. Let's say you chose 1 instead. If we chose 1, then we would be going up to this point right here. And this number 4 over here is 4. All right, cool. So our force equals 1. Our acceleration is 4, and 1 divided by 4, 25. So our answer is the same. So if you chose this one here, 0, yeah, obviously that one won't work. If you choose 0, 0, that won't work. It's the only one that won't work. But you have to choose a non-zero number, okay? So that will help you. All right, let's move on to the next questions, which are on the back. They happen to be bigger. So let me see if I can zoom in. Aha, I did. All right, it says use the picture below. What is the net force acting on the object? Remember, net force is when we add up all the forces together and find out what direction is it going to go and by how much. So we have the air. We have the force of air pushing up, apparently, on this box, and we have gravity pulling it down. Okay, so we basically, you could say it like this, air really shouldn't be pulling, it should be pushing. Okay, this is kind of a bad diagram. The 200 newtons, I would say, is here, and this is our air friction. So I'm just going to put air here. And that makes more sense, right? Okay, as it's going down, the air is pushing it up. Okay, who's going to win? Is the box going to stay up or is it going to go down? Well, clearly, the 600 is greater than the 200 newtons, so we know that it's going to go down. But will it go down by the full 600? No, because 200 of it is being fought against it, going the opposite direction. So basically what you would write over here is 600, and let's say that up and to the right are positive. Okay, so these are our axes and our directions that we're using. So if 600 is to the right, or down, sorry, if 600 is down, so that's going to be a negative 600 newtons, okay, plus a positive 200 newtons, then that means we have a negative 600 and a positive 200, which means we're going to have a negative 400 newtons of force. And that's going to be our F net. The negative doesn't mean anything bad. It just means the direction that it's moving. So if we said that positive is up, then that indicates that we are moving in the down direction. That's all it means. It's nothing scary. Negatives are not bad. They just need to be identified. All right, so let's look at number 9. Calculate the potential energy of a 15 kg bowling ball suspended in 10 meters above the surface of the earth. So it says calculate the potential energy. So there's our question mark. PE equals question mark. We're going to use a formula with PE in it. We know that kg is mass, and we know that meters is for distance. What kind of distance? Well, it says it's suspended above the surface. So we know that's going to be delta y, or we could also write the letter h because that means vertical as well, right? And we want to know potential energy. Well, the formula for potential energy is usually mass times gravity times height. Do we have those variables to be able to solve with? We have mass, and we do have height, and we know what gravity is on Earth is 9.8. So yep, we do have everything we need. Let's go ahead and just put in our numbers and solve. So for PE, for potential energy, our mass was 15, our gravity was 9.8, and our height is 10. So if we were to put this in here, I have basically 150 times 9.8 because 15 times 10 means you move the decimal over once. But you will be putting it in your calculator all at once. So 15 times 9.8 times 10, and that'll give you 1470. That's your answer. Oops, sorry about that. That's your answer. So you're going to have 1470. Remember, energy is measured in joules, and that's your final answer, equals P. Ta-da! All done. Very, very easy. All right, number 10. What is the force of gravity? So I'm going to stop and I'm going to underline the force of gravity. So they want F of G. And we know that the force of gravity is mass times gravity. That's the formula we're going to use because the force of gravity variable is inside the formula. Therefore, we can solve for it. Okay, and we have a 600 kg is mass. And that's mass 1. And there's another object here right next to it. So that's going to be our mass 2. Remember, when we have more than one number that has the same units, we need to identify the difference between them. So here's the first object, and here's the second object with a distance of this. And that's going to be our radius, or our distance in between. So you could put a D, or you can put an R for radius. It just means the distance between them. So we're going to make this was our simplified formula, but they're asking for more than just one object. So we're going to do a little drawing here just to indicate the difference, what they're talking about. I basically have a radius between these 2 points, the center of the 2 points. This is going to be my radius, and this is going to be my mass 2 and my mass 1. Of course, you can make that mass 2 and this mass 1 if you wanted to. It wouldn't make any difference. You're just looking for the attraction between these 2 points. All right, so we're saying we're going to be using a different formula then for the force of gravity. We're going to say that the universal gravitational pull between a proton and an electron times mass 1 times mass 2 is all divided by the square of the radius, okay? So don't forget, you're going to have to square that number, and that does make a difference in your answer, a huge difference, so don't forget to do that. So what is the number for the capital G? The capital G is 6.67 E negative 11. Yep, that whole thing. Times the first mass, which is 600, times the next one, which is 3.5 E5. Remember, the E stands for times 10 to the negative. Is that negative? No, there's a positive 5. So basically, I could write 3.5 times 10 to the 5th, or I could write E5. I'm running out of space here, so I'm just going to put it like that. Okay. And then, of course, all of this is supposed to be divided by my radius. And my radius said it was 4.5 E6. And all of that must be squared. Big deal, right? All right, so if you use your parentheses properly, you can put this all in at one time. So let me show you how to do that. I'm going to move my paper out of the way so I can see what I'm doing while I'm putting this in the calculator under the video. So 6.67, second button. And then here's my E. You can see the little letters there. That means times 10 to the exponent. So all you have to put in is the exponent number at this point, which is a negative 11. Parentheses, new parentheses. And then you're going to put 600, parentheses, new parentheses, 3.5. And then your E, and then a 5, parentheses. You can hit the divide by button. We can do this all at once. And we're going to put 4.5 E6, parentheses squared. Remember the square button's right here. Okay. All right, hit enter. Oh, that looks scary. It's really not. Really not. If you don't like that, then hit the second button. We want to fix the decimal places. And if you notice down here at the bottom, it says, let's fix that decimal place. We push that, and it gives us this. How many places do you want to see after the decimal? 1, 2. For me, for us, we would like 2. And that makes it look a lot better. And plus, it rounds the second digit for you. So 6.92 E negative 16 is your answer. So we're going to write that down. Let's just put it right here. Or you know what? Let's put it up here. We're going to put 6.92 E negative 16. Okay. And remember, this is the force of gravity. So if it's a force, that's going to be in newtons. It's going to be in newtons. You could have also wrote 6.92 times 10 to the negative 16 power. It would have been the same answer. Okay, so whichever way makes you feel more comfortable. Okay, those are the two choices that you have. So you do you. You do you. Got 2 more questions left, and then we're going to be done. So let's get to it, shall we? And let me just try to get my camera a little bit zoomed out so you can see the whole question at once. Right there. Yeah. All right, a force of 15 newtons. 15 newtons is exerted on an object moving 25 meters. So we know that 15 newtons is a force. I'll put an F right here. Moving at 25 meters, so that's going to be a distance. You know what I'm going to do also to make this a little bit easier to pay attention to. I'm just going to get rid of all that other work so you're not freaking out on me here. Wham, bam, thank you, ma'am. All right, cool. All right, so what is the work being done on this object? So there's our question. What is the work? Work equals question mark. So that means we need a formula that has the W in it. So let's write our formula for work. Work is force times distance. And you can look that up on the cheat sheet that I gave you to help you out with formulas, abbreviations, and units. All right, that will be on your desk on the day of the test. So work is force times distance. So what's our force number? 15. What is our distance number? 25. So what is our work number? Well, it says to multiply those two, so let's do that. 15 times 25 equals 375. And oh, look, you're done. So what do we put at the end? That's called our unit, and we use joules because work is a form of energy that we used. Okay, we used up this amount of energy to do the work. So it's in joules. Force is newtons, okay, and work is in joules. One more. Number 12, right? Yep. So for number 12, it says I've got a 15,000 kilogram car. Kilograms is mass. Comes to a stop after braking. So if it's stopped, what kind of velocity do we have? You're right. The velocity is 0. The brakes do this much work. See? So we're going to label that as W to stop it. What was the car's velocity when it began to stop? So they want V equals question mark. So I have mass, and I have work, and I have velocity. Did you know that if work is energy, we can also call it kinetic energy because it's also energy? They're all the same thing. Yes, ma'am. Yes, sir. So we're going to use the KE formula to solve for velocity because KE is equal to 0.5 times mass velocity squared. All right. So if our KE number is 10,000, make sure you can see this. Yep. 10, 1, 2, 3 is equal to our 0.5, which is half, of our mass, which is 15,000. 1, 2, 3. So we're going to take half of 15 in a second, times our velocity squared. That's what we're solving for. We're going to remember, we're going to have to square root because we got to get rid of that 2. To get rid of a square, you do the opposite, which is a square root. So half of 15,000, or we can just put that in our calculator and divide the whole thing. So let's do that, shall we? 0.5 times 15, 1, 2, 3 gives us 7,500. Okay, so we're going to put 7,500 here because that's how much this equals. So these all cancel out. What I do on one side, I do to the other. So 7,500 goes here. So now we're going to divide these two numbers and find out what our V squared is. So I'm going to do 10, 1, 2, 3, divided by 7,500, which gives us 1.33. So what we're saying is that V squared is equal to 1.33. So we're not done. Remember, we got to get rid of the square. So square root it. That cancels with that, leaving us with the square root of 1.33, which is 1.15. Okay, so the square root of 1 is 1, and the square root of 33 is 0.15. So 1.15 meters per second is our velocity. That's how fast it was going when it began to stop. Pretty interesting stuff, huh? You'd think you'd never be able to figure it out until you have the formulas, and then it's like, I can do this. Yes, you can. Anybody can do it if they know what the formula is. And as long as you can identify your variables with the kg or the ms, that's your 2 tricks to figuring out your physics problems. It's just identifying the variables and identifying the formula, and then you're set to go. You just got to know your algebra. That's pretty much it, guys. Think that was everything. I've already gone through. Here's number 1 in case you need it. I don't know if I put number 1 up on YouTube, so I'm putting it out in front of you right now so you can take a look at it and go, ooh, of course it is. All right. Have a wonderful day.